All right, so today we're getting into continuing to look at continuity. And so yesterday we really were looking at it all when we were dealing with graphs. So here I've given you a graph and the piecewise function that creates it. And the question here is this particular function continuous at x equals 2? Looking at the graph, is it? Is it continuous here at x equals 2? No. All right. What type of discontinuity would we call that? Jump. Yes, that is a jump discontinuity there. But now, that's the easy part, is looking at a graph and saying, well, yeah, I can see that it's not the same. But how could we prove that mathematically? In other words, without just saying, yeah, I made the graph and I looked at it. How else could we prove that that is actually going to be a discontinuity there at x equals 2? And so one possibility then, I heard we could plug that value of 2 into both equations, and we could see that this one would give me 5 and this one would give me 3. They give us different numbers. Is that enough to prove every discontinuity? What if we had a hole at a point? Well, if I just plug the number in, I'd get the same thing in both of them, but it wouldn't tell me there was a hole, right? So how would I be able to prove it there? There's some details, there's some finickiness to it, right? And so that's what we're going to look at today, is that finicky piece. So what I'd like you to do, please, is to write this into your notes. This you should already have. The bottom part, please add into your notes right now. All right, so a little bit about what you're getting down here. First of all, we already got this definition yesterday, and we could actually use that definition just as it is in order to prove or disprove whether something is continuous at some number, some value, a in this case we're calling. But these three details, these three steps, basically just get into more detail on that. For instance, if I'm going to say that this limit is equal to something, or if I'm going to say that this f of a equals something, they have to actually exist. You know, if f of a does not exist, then of course there's not going to be a value there, and therefore we cannot set it equal to anything. Also, if the limit doesn't exist, same thing. So if you go through, find the limit, and you end up with a DNE does not exist, then you can say, okay, well, then it must not be continuous. Finally, if both of those exist, then we can actually plug it in and test, is the limit equal to the value at that point? Now, when we find that limit, our reasoning can get a little circular if we're not careful. Like, how do we know whether the limit exists? Well, it wouldn't make sense to say, well, the limit for this particular function does not exist because it's not continuous. Because notice, this is trying to prove whether something is continuous or not. We can't say it's not continuous because it's not continuous. We have to have some other reason. So how do we tell if it's actually continuous as x approaches a? Well, we could actually test two separate limits. If the limit as x approaches a from the left is the same as the limit as x approaches a from the right, then we can say that the limit as x approaches a exists. And it's the same thing as whatever both of those values are. If those two values are different, the limit from the left and the limit from the right, then you know you're looking at some sort of a jump discontinuity. And so you can say they're not continuous because the limit does not exist. So we're now going back to this problem. Now, this is the same system or the same piecewise function that we saw earlier. And we saw the graph and we saw, hey, there's a jump discontinuity there. But without having to make the graph, how do we do it? So that's what we're going to do here is we're just going to walk through and see how these steps would apply to just starting with this equation. I'd suggest that you write this into your notes as we go through it. All right, so I'm looking at that piecewise function. And the first thing we need to do is we need to figure out what is f of 2. Well, that already makes us have to make a decision. Because the value of f of 2, we have two different equations here. Which equation am I going to be plugging the 2 into? The first equation or the second equation? The first. Why? Because I need to actually look over here at these domain restrictions to see which one is actually dealing with 2. You notice that this is the one where the 2 is actually part of the function because it's less than or equal to. The other one is just greater than. So 2 is not a part of that function. All right, so that means I'm plugging into the first. So I'm going to go ahead and do that. F of 2 equals 2 times 2 plus 1. All right, so 2 times 2 is 4, plus 1 is 5. So f of 2 exists. How would I know if it didn't exist? Well, if there were none that included 2 over there, if none of those domains included 2, that would be a sure sign that f of 2 did not exist. All right, but it does exist. We found it. So now we go on to the second part, where we're finding the limit at 2. So first thing I want to do is I want to figure out what is the limit as x approaches 2 from the left side. So from the left side then, which equation am I using again? The first or the second? Well, which one shows the values that are less than 2? The first one again. Because that's a less than or equal to 2. X is less than 2. And so I'm going to be finding the limit on that line as we approach it. Now, a little side note, a technical note, one of those detaily things that you don't necessarily have to think about consciously all the time, but is important. Remember yesterday when we looked at, hey, all of these functions, basically all of the function families you know, are continuous across their entire domain? Because this is one of those function families, it's a polynomial, more specifically a line. We know it is continuous across its entire domain. So we know that not only will it have a value at 2, but at every value to the left of 2 that's in its domain. That's one of those technical things that, again, you don't necessarily have to worry about all the time, but just letting you know why we can do this. So since it is continuous from the left-hand side approaching 2, I'm going to take that 2 and I'm going to plug it into that equation. So I'm going to go plug that into the 2x plus 1. Basically, it's working out to be the same thing I just did. 2 times 2 is 5, or 2 times 2 is 4, plus 1 is 5. Now I need to find the limit as x approaches 2 from the right-hand side. Now, notice from the right-hand side, that's where we're greater than 2. That's the second equation in our piecewise function. So now I'm taking a look at the 3. So the limit as x approaches 2 from the right-hand side at 3 equals what? 3. Yeah, because anytime it's a constant, it just equals itself. Because think about what the graph would look like. That's a horizontal line. No matter what x value I'm at, the y value I'm approaching is 3, because it's always 3. All right, so having done that, I did all that work, the limit from the left-hand side and the limit from the right-hand side, so that I could then just answer the question, what is the limit as x approaches 2? What is the limit as x approaches 2 in this? It doesn't exist. Yeah. Because I got two different numbers here. I got a 5 and I got a 3. So because that limit does not exist, I could then actually proceed straight from there to say, therefore, it is not continuous at x equals 2. However, just for the record, if we did find that we actually had a value, we would then take our two values and set them equal to each other. So like that last line would be f of 2 equals the limit as x approaches 2 of our function here, so of y. And we would set, okay, so we found f of 2 was 5, and the right side, yeah, it equals d and e. That's why we don't have to actually do this. But if we got a value, you would plug in whatever that value was there, and if that is true, then you would conclude continuous. So basically, if it satisfies all three of those steps, you know it's continuous. If it fails any one of them, there is a discontinuity. And so it is not continuous in that case. All right, so here's the next function that we're going to be working with. And for this one, I've given you the graph just in case you need something to kind of lean on, but I want you to prove whether this function is continuous at x equals 2 just using our continuity test to prove it algebraically. And as you're working, one of the things I hope you're noticing is you're often having to go back and make a decision, which equation am I dealing with as part of this piecewise function? Is this talking about the first, the second, or the third piece? And to know that, we're always looking at those domain restrictions that go down the right-hand side. So always be paying attention to those. All right, so now let's go ahead and work it out. We got 3 things that we have to do here. We first have to check and see what is the value of f of a. So I'm actually going to do f of 2 here. And that means I got to decide which function or which equation I'm plugging it into of those 3 equations that make up our piecewise function. So which of those, equation 1, 2, or 3, is valid when x equals 2? Yes, it is equation 1 because that's where we're told x is less than or equal to 2. So I'm going to be plugging it into that first equation. So that means I'm going to be doing 2 squared plus 1. And so if I do 2 squared, that's 4. 4 plus 1 gives me 5. Just like the last one. They won't always be 5. I know, shocking, right? All right, so that one worked. Nothing there that's going to tell us anything about it being continuous or not yet. All right, step 2. We need to find the limit as x approaches 2. Well, in order to do that, then, I have to find the limit as x approaches 2 from the left-hand side, and the limit as x approaches 2 from the positive side. And I need to see if those two are going to give us the same thing. So, the limit as x approaches 2 from the left-hand side, which equation am I plugging into there? Which one shows the points that are to the left of 2? Is that equation 1, 2, or 3? That is equation 1, again. Because the x's are less than 2. That means to the left of 2. All right, so if I plug 2 into that equation, I end up with, of course, 5, because that's the one I just did up here. So I know that's going to give me 5. Now if I do it from the positive side, so the limit is x approaches 2 from the right-hand side, that is for the x's that are going to be to the right of 2. And notice, here we have x's that are greater than 2. All right, so that means I got to be going into that equation. So I'm going to be going a negative 1/2 times 2 plus 6. Negative 1/2 times 2 is a negative 1. Negative 1 plus 6 is 5. So based on that information, what is the limit as x approaches 2? Does it exist? Yes, it does. The limit as x approaches 2 does exist because it's same from both the left and the right. It is 5. All right, so having done that, then we just have one last step. The last step now is to decide, does f of 2 equal that limit? The limit as x approaches 2 of g. Does f of 2 equal the limit as x approaches 2 of g of x? Well, that gave us 5 equals 5, so yes, it did. So then you would conclude as a final answer, it is continuous. And so that would be your final answer. This is all just work. Your final answer is, yes, they are continuous. All right, now having said that our answer here is that they're not or that they are continuous, I do want to clarify one thing. What are we actually saying when we say yes, continuous here? Are we saying that this whole piecewise function is continuous? No, we're not. What is continuous? It's only continuous at this one value that we're dealing with here. So it's, remember we were asked, is this continuous at x equals 2? All we're concluding here is saying that the function is continuous at 2. We're not saying the whole thing is continuous. If we take a look back up at our graph there, that we have there just as that extra reference, you can see, yes, it's continuous there when x is 2 because both of them are approaching the same point. And there actually is a point there. But here, notice there's still a jump discontinuity. So we're not saying the whole thing is continuous, we're just talking about that one point. All right, lastly, I'd like you please to find this one. Is this function continuous at x equals negative 3? And there you have the function definition. Do all the algebra, no graph to rely on here. All right, so to prove this, the first step is to figure out what f of negative 3 actually equals. And so I got to take that negative 3 and plug it into one of those three pieces of my piecewise function. Which one does it go into? The first, the second, or the third? Well, we're looking to see where it can actually equal negative 3. That looks like that one right there, because there negative 3 is less than or equal to x, so you're actually plugging it into the second equation at this point. So I'm going to go negative absolute value of negative 3 plus the 5. That gives me a negative 3 plus 5, which gives me 2. So that's your first step. Having completed that, you then are going to proceed and go on and figure out what is the limit from the left and the right to figure out the actual limit at negative 3. So the limit from the left, as I approach negative 3, which equation am I using if I'm coming from the left side? The first, the second, or the third equation? The first. Yep. Because that's where the x's are less than negative 3. And notice it's actually touching on that negative 3. It's just going to the left of it, but not including the negative 3. All right, so if I look to see where that hole is, because this one, if I graphed it, would have a hole at that end, I would end up going negative 1/2 times the negative 3 minus 1. Well, the negative 1/2 times the negative 3, that gives me 1.5. 1.5 minus 1 gives me 1/2. All right, next one. The limit as we approach negative 3 from the positive side. Which equation am I going to be using there? 1, 2, or 3? 2. Yep, it ends up being this one, because there the x's can be greater than negative 3. They can be above it, so that means to the right of it. So then I end up plugging it into there. That's actually the same thing that I did right up here. So I get 2. So I did that work and I discovered that the limit from the left is different from the limit from the right. Therefore, the limit as x approaches 3, or I'm sorry, x approaches negative 3, does not exist. Therefore, is this continuous? No. We can conclude right there that it is not continuous because that limit does not exist. Now, knowing that it does not exist, a little bit of follow-up question with that. What type of discontinuity is it at negative 3? It'd be a jump, yeah. Because the limit from the left is giving us a totally different number than the limit from the right. So that means it must be making a jump there. All right? And then again, just to emphasize and remind you, what are we and aren't we saying with this? All we're saying here is that at x equals negative 3, it is not continuous. We've only really proven anything just for that one x value. We haven't proven anything about any other x values or about the whole function as a whole. Now, just connect it to the graphing that we've been doing. if you'd graphed it, this is the sort of thing you'd be looking at. And notice we can actually see that jump taking place there, because there's our -3. We can see that jump taking place, and why, if we had just looked at the graph, we also could have come to that same conclusion.